This video on thermodynamics is going to cover the concept of enthalpy and what are the different signs of the enthalpy and the potential energy diagrams you use to determine if a reaction is endothermic or exothermic. So first we need to talk about the first law of conservation of energy, which states that energy cannot be created or destroyed. It's only going to change forms. So it's just going to be transferred between a system and the surroundings. So we have a diagram here that shows you the system. The system is what's inside the piston chamber here. And there's basically a reaction going on in there. And the surroundings are the outside of the system. So the chamber and the piston, those will be considered the surroundings. And anything beyond that. So if the reaction is going to release some energy, the energy is going to be used as work on the system or on the piston, and then we're going to see the piston move, and possibly we'll see some temperature changes and the volume might change. So the energy is going to be conserved by transferring it from the system to the surroundings or vice versa. So when we're talking about enthalpy, enthalpy is the measurement of heat flow. And it's the exchange of heat from the system to the surroundings and vice versa. So really it's the change, and that's what a delta sign means. A delta is a state function, which means that we're just looking at the difference of the enthalpy of the products, the final things, compared to the enthalpy of the reactants, the initial things. And if the products have less energy than the reactants, or less enthalpy than the reactants, then that means there's going to be some extra heat, energy given off as heat, and that's going to make the reaction exothermic if the products are less than the reactants. So looking at this, if reactants are greater, the value, the magnitude of the reactants are greater, you would end up with a negative sign. And exothermic reactions have a negative sign for their enthalpy. If the converse is true, if the reactants are less than the products, then you would end up with a positive sign, and that would be an endothermic reaction. And the delta H would be positive for endothermic reactions. So let's look at a couple of situations, reactions, and talk about what's happening to their heat. So a chemical reaction that gives off heat to its surroundings is said to be what? So if we are giving off heat, meaning heat is going from the system to the surroundings, then that reaction is exchanging heat out, and it is exothermic. And because the reaction is exothermic, it would have a negative value for the delta H. So reactions that give off heat are exothermic, and they have negative delta H values. Reactions that are taking in heat from the system, from the surroundings to the system, meaning they're absorbing heat, the surroundings are going to get cooler, or you're going to feel a temperature drop, and those would be endothermic, and they would have positive delta H's. As an ice cube melts under atmospheric pressure, is the process endothermic or exothermic, and what is the sign of that delta H? So what are we talking about? We're talking about a reaction in which ice is melting. So we have water that is solid, and it is becoming water that is liquid. So how is that doing? Well, we're having a phase change. And how does water go from a solid to a liquid? It's going to have to take in heat. Think, how do you melt ice? The ice is going to absorb heat from the surroundings. So as the ice absorbs the heat from the surroundings, that would mean it's going to be endothermic. And as a result, if it is endothermic, delta H is positive. And so there's your explanations. Melting, changing from a solid to a liquid, requires heat to be absorbed by the ice from the surroundings, and therefore is endothermic. The sign of the delta H is positive. So let's look at some graphs that you might experience on the AP exam that will show you graphically the progress of a reaction and allow you to determine things about the enthalpy of the reactants and the enthalpy of the products. So if you're looking at a graph like the one we have here on the right, this is a graph of potential energy, tells you on the y-axis its potential energy, compared to the progress of the reaction, which is telling us that what do we start with when we are beginning a reaction? Well, these are the reactants. And over here, these are the products. Now, what's happening here in the middle? That's the progress of the reaction. So when we're looking at a graph like this, we're going to have to determine and possibly calculate if the reaction is endo or exothermic, and then what's the sign and the value of the delta H. So here's what we know. We know the level on the graph of where the reactants are. They are at 40. And we know the level on the graph where the products are. They are at 20. Okay? And so we can look at the difference between the products and the reactants. The products have a potential energy of 20 kilojoules. The reactants have a potential energy of 40 kilojoules. And 20 minus 40 kilojoules gives us negative 20 kilojoules, which tells us that this reaction is exothermic because the delta H is negative. And we can see that in this reaction because what are we going to do? We're going to put some energy into this reaction to get it started. That's what this hump is. This is the energy that we're going to put in to get it started. We will call that activation energy. EA. And then what's going to happen once we get the reaction started? We're going to get back some energy. And this is the energy that's going to be returned to us. And so what's the difference? Well, we put in 60 kilojoules of energy, but we got back 80 kilojoules of energy, which meant there were 20 extra kilojoules. And where did that extra energy go? Well, it just had to get released by the reaction to the surroundings. And that's where this difference is. Okay. But when we're doing the calculation, we don't have to use activation energy back. We can just start with where the reactant started and compare it to the products, and we can subtract and we can get the enthalpy of the reaction. So let's look at a practice graph. We're given a graph over here. Again, it's potential energy. It doesn't have the units on there, but note that it's usually in kilojoules or sometimes joules. And we also have the reaction pathway, which means the reaction is proceeding. And they even tell us this. We're proceeding from the reactants to the products. And it says, given the following graph, what is the reaction endo or exothermic? Justify your answer with a calculation. So we're going to put some energy in, we're going to get a little bit of energy back, and what's the difference? Well, this is the typical graph of an endothermic reaction. We had to put in a bunch of energy. We got some of it back, but not all of it, which meant ultimately we had to put energy into this reaction. And how do we put energy into a reaction? It's in heat, okay? We can also calculate it, so we can look at the delta H values with this graph. Not all graphs are going to have the values on the y-axis, but this one does, so you can use it to calculate it. So what is the enthalpy of the products? It would be 300. And what is the enthalpy of the reactants? It is 100. And so 300 minus 100 gives us a positive 200. And that means this reaction is endothermic, because the enthalpy is positive. Then it says indicate what values are represented by A, B, and C. So what's A represent? Here's A. A represents the amount of energy it takes to get to the top of the hump, which is the activation energy. All right, what's B represent? We're going to come back to B in just a second. What's C? C is the difference between the reactants, which are down here, and the products, which are up here. So what does C represent? Well, it represents the thing we just calculated. It's the delta H, which is 200. Now, what about B? B is one of those things that a lot of times people look at and go, well, it just is the difference between the top of the hump and the products, which that's true, but it also represents something else. So what if this reaction were going in the opposite direction? What if the reaction were going in this direction? What would B be for that? B would be the activation energy of the reverse reaction. So that helps you a little bit with reading enthalpy diagrams and showing you what the different parts of an enthalpy diagram, and I hope that helped. The answers on the answer slide we just went through, but as long as you can read an enthalpy diagram and look at an enthalpy diagram and recognize that it is, if it's endo or exothermic, that's going to make your life a whole lot easier. So in general, if we are looking at enthalpy diagrams, we just got to look at the humps. So here's an enthalpy diagram that looks like this. And we're going to draw another enthalpy diagram that looks like this. And what can we say about these two enthalpy diagrams? Well, here the reactants are less than the products. So if we said products minus reactants, we would get a positive sign, and this would be an enthalpy diagram of an endothermic reaction. And here, when we look at the second graph, if we look at the products, which are down here, and compare them to the reactants, which are up here, and the difference between those two things would be the delta H, and in this reaction, the delta H would give us a negative value, which would end up being an exothermic reaction. Now, one thing that will show up occasionally will be they'll give you a reaction and they'll give you a second graph on it. So let's say we had a second graph like this. And they'll say, what's the difference between those two graphs? Well, the only difference between the blue graph and the green graph is the activation energy. And so what's represented by the green graph? The same reaction that has a lower activation energy, and that is caused by a catalyst. So if you see two graphs like that and one with the same exact graph with a lower activation energy, that's about a catalyst. Hope that helped.